So far we've talked about two ways of finding work. The first is that work is F delta x cosine theta, and that allows us to find the work from a force. And the second is that work is just the change in energy, and that really gets at the idea of what work really represents. But we do have a third way of finding work, and that is with a graph. So on a graph, work is also the area under the curve on a force versus displacement graph specifically. So why exactly does this work? When we take that area under the curve, when we integrate, is the calculus way of saying it, what we're really doing is we're really doing y times x. We're multiplying whatever quantity is on the y-axis by whatever quantity is on the x. So if we do force times displacement, that gives us work. That's essentially this equation up here. Okay. The key advantage here for using a graph is a graph allows us to deal with a non-constant force. Right? If we're using our F delta x cosine theta, we have to have a constant force. But if we have a graph, we can deal with a changing force like we have here. We can have a force that goes from 0 to 12 newtons and then back down to 0 as an object moves a distance of 5 meters. And we can still calculate the work done using that graph by finding this area under the curve. Let's do a quick practice problem with this. So we have a graph here showing the forces acting on a 5 kilogram box as it's pushed 5.5 meters across a frictionless floor. And we first want to figure out the work done by the force. So with this graph, we're going to be thinking about area. And what I'm going to do is I'm going to go ahead and break this up into two different areas, a rectangle and a triangle. And I'm going to find the area of each, and that's going to represent my work done. So for that first shape there, that triangle, the area is 1/2 base times height. So 1/2 2 times 8, or an area here of 8 joules. All right, it is a work, so the units are still joules. For the second shape, it's a rectangle, so the area is just base times height. The base here goes from 2 all the way to 5.5, so it's 3.5 times 8, or 28 joules. So my work done here is just going to be the sum of those two, which is 36 joules of work. For the second part, we're told that the box is initially at rest and there's no other forces acting on it other than the one shown. We want to now know what the velocity of the box is. So think for a second about what this work here really represents. Work represents the change in energy, and in this case, this box being pushed is going to gain kinetic energy. So we can say that the work done is the change in kinetic energy, which is the final kinetic energy minus the initial. Okay, any change is always final minus initial. Since we're initially at rest, that initial kinetic energy is 0, which means that our work done here, 36 joules, just equals 1/2 mv squared. Okay, so we can say 36 equals 1/2. Our mass is 5 times v squared, and we solve for our velocity, and it ends up being 3.8 meters per second. Okay, so we can use that work done, because we know that work becomes kinetic energy, to solve for the velocity. We now have a conceptual problem with the same basic idea. We want to rank the net work done in each of the situations below from least to greatest. So we'll start here with set A. We have 3 graphs, so we're thinking about area in this case. Okay, and so the area for our first graph here is going to be that triangle there. Our area for that second graph is going to be that rectangle, and then the area for the third graph, we have one rectangle here above the axis and one rectangle here below the axis. And so we want to think about comparing those areas, because that really is going to compare the work done. So the easy one to look at here is just comparing A and B. B clearly is a bigger area than A. It has the same base and height, but one's a rectangle, one's a triangle. So we can say that A definitely has less work done than B. Looking at C might be a little bit trickier, but if you think about what we did before with area, we know that area above the axis is positive and area below the axis is negative. Okay, so that means that we actually have a negative amount of work done here, and since those two areas are the same, the work done by C ends up just being 0. So that one is the least. Now you might be thinking, how is that possible? This would be a case where initially the force and the displacement of the object were in the same direction, all right, and so positive work was being done. But once we switch down to here force and displacement end up being in the opposite direction, and that leads to a negative amount of work being done, taking energy away from the object. For the second one, we're given a few different situations, and so what I would think about here is work is the change in energy, and so let's think about how our energy changes. So for the first one, we start out at rest, so that's a kinetic energy there of 0, and we speed up to some speed here, v, so that's going to be a kinetic energy of 1/2 mv squared. For the second situation, we start out already in motion at a speed of v, so our kinetic energy is 1/2 mv squared, and we speed up to a speed of 2v, so now it's 1/2 m times 2v squared, okay, which ends up being 1/2 m times 4v squared, all right, you have to square both the 2 and the v, and so our overall kinetic energy now is 2 mv squared. And for the last one, we start out traveling at some speed of v, so we have 1/2 mv squared as our initial velocity, and our final ends up being 1/2 m times negative v, because we rebound. However, when we go and square that, we're left with 1/2 mv squared. So that means that the work done in each of these situations, for C, it's just going to be a work of 0 joules. Okay, for B, if we do final minus initial, it's going to be a work done of 3/2 mv squared. And for A, again, final minus initial, it's 1/2 mv squared. So we can clearly see here that the ranking is actually the same as the first. C is less than A is less than B. Once again, we have a situation here in C where no work is being done, and there's two important points about this. Number one, in terms of a physical situation, okay, this would be very similar actually to the graph we see in C. If an object's initially traveling to the right and slowing down, force and displacement are in the opposite directions, and then it rebounds back to the left and is speeding up. In that case, force and displacement are going to be in the same direction. So we have a negative amount of work done initially, and then we do that same amount of work but positively to get it back to a speed of v. Overall, no work is done. The other important point that this brings up is that energy is a scalar. Okay, we don't have a direction associated with energy. Okay, so if you're traveling at a speed of v west versus a speed of v east versus a speed of v north, it doesn't matter what direction you're traveling, your kinetic energy is the same. And in this case, this object was traveling at the same speed in both cases. All that changed was the direction. And since energy is a scalar and direction does not matter, then the energy of the object did not change. All right, one last concept to talk about here before we start really applying energy, and that is the idea of heat. Okay, so heat's a pretty complicated concept. We could spend a long time talking about heat. In fact, there are entire courses dedicated to heat called thermodynamics. What we're going to do is have a very simplified, basic working definition of heat, and that is that heat is the change in energy that results from work being done by friction or air resistance. That's not the full story, okay, but when we have frictional forces acting on objects, when we have energy lost, okay, that energy has to go somewhere, and the place that it goes is heat, okay? If you have an object sliding across a floor, all right, and friction is acting on it, all right, and taking away its energy, what actually ends up happening is a small amount of heat is generated, and it actually increases the temperature of the object and of the floor, all right? You can really feel this if you take your hands and you rub them together, okay? There's frictional forces between your hands being rubbed together, and you can feel the heat being generated in that case. All right, so heat for us is going to represent the energy lost when we have things like friction, air resistance, etc. It is a simplified definition, but it's going to work for our purposes in this class.